Draw the diagram. The weight of this one is 100 newtons. Okay, 100 newtons. The diagram is given there, so you can make use of it. 100 newtons. Okay, and then what is given to you? If the diameter is given to you 20 mm each, right? Both are 20 mm. Both are 20 mm. Both are 20. Let's do that. Arrow. Okay. These are the data given to you to mistake in doing calculation and also in understanding, right? Okay. These are the data given to you. Two members, right? They are hanging some load. What would be the stress developed? They are force members, right? They are what? They are fixed into the wall. Imagine they are fixed into the wall at A and B. What would be the stresses developed in these members AC and BC, right? As usual, you can start with given data. You must always follow the strategy that was given to you. 5 steps, 5 steps. Don't forget, given data. Let me write in blood. Given data. You are given with the diameter of the cable. Diameter of cable, right? You can immediately find out the area if you want. 20 mm, right? Or otherwise, you can call this as 0.02 meter, isn't it? 20 mm or 0.02 meter. Hence, you can find the area later on. And then the supports are fixed and this carrying a weight. The weight is given, load at P, and just say P. P is equal to 100 newtons. Then what is given to you? Angles are given to you and so on, right? Any other data given to you? Only this information, right? Moving on, it is asked to calculate required question, required answer. Required answer. Required answer. You need to find the stresses in members, right? Normal stresses. Why I say normal? The load is acting perpendicular to the cross section, right? Normal or shear we will find out later on, but let's find out the stress. If you find out the stress, you will know in this reaction by loading, it may be either extended or both members are extended. Same side is extended, so it is a normal stress. There is no way it is getting shear in this situation, right? Due to the weight, there is a chance that if the weight of the load is increased, right, or the load overcomes the force existing on the member or the stress created by the member, then automatically it will get extended. So it is a normal stress which is in tension. Tensile stress also you can call this as, right? And then required answers are forces in, or not forces, stress developed in AC and BC. Sigma AC and sigma AB are asked. Okay, this is the required answer. Come on, moving on to solution. Solution. Okay, please make the correction. It is AC and sigma BC, not AB. Please make note of this correction. Please follow carefully, otherwise you can. Okay, you can call in anyway. Try to understand these terms. Sigma n, let it be sigma n. Sigma T, if it is tensile, also you can use it. If you know already it is purely a tensile force. Q over A. Now we have, you can also call this as force over area, right? Or you can also call us normal force over area. Also possible. Okay. Units important. Okay. Borne by M into G, right? All of you know this equation, right? And we can call this as 1 Newton, right? If you call force as 1 Newton, right, then you may have this as 1 kg. This is in terms of kg, mass is in terms of kg, and G is 9.81 meter per second square normally, or 1 Newton is equal to some recall on what you studied before. If this is 9.8, right? When I approximate it, it may be approximately equal to 10 kg meter per minute, keeping the calculator all the time. For a quick 1 kg for every meter run times, or for every meter run over time square or second square, right? Bear in mind when we go for some kind of demonstration experimentation, you need all these colloquial terms just to recall at this point of time, right? Now coming to our, remember these units are 10 power 6 of Pascal, right? 10 power 6, or you can write it as micropascal itself for better understanding, otherwise they confuse with other terms. Micropascal. So these are the things you have to remember and just to recall the unit system. Now let's take our solution. Our solution started already. We'll just recall code, right? And at A, start with A. Point A, there is a common member, another member at point B, and this is fixed, right? Like this. Like this. Like this. You can have a different color. Angle of, it is making an angle of, I take black color, and this point is C. Load, everything we marked already. Now reactions, okay? Because of this load at this point, because of this load at this point, you may have, because of the load acting at this point, you may have a reaction followed by, it's a vertical one, right? It's a vertical supported by this. Because of that load, there will be a reaction. B, I call this as RA, or for convenient way of marking, I take the shear force as BAB, the member AB. And then similar to this one, because it's downward, it may be upward like this, BB, BC, okay? At point, we will see what are they one by one. And I can repeat once again. Horizontal and vertical, we cannot take it as it is, isn't it? It is difficult to, what do you call, I don't know, this is equal to the system will collapse. Better you draw the diagram separately so that you can follow the answers. Now we can apply equilibrium equations by applying, you can even write down, by applying, always write this statement, by applying fx equal to 0, sigma m equal to 0. Let me start with number 1, which is sigma fx. In x direction always comes first, although I wrote y first, x direction first. It's always like this. Number 1. Remember these points, okay? Remember it's like this. AB, right? This is VAB, and the angle of this one is 30 degree. Now I need the x component only, right? And this is x and this is y, right? Assuming that the x direction is in this way. Initially we assume the x direction to be this way. Then we will decide whether it is the correct answer or not, right? And then y to be downward, because upward. The load is acting downward, so I can assume the vertical component to be upward. Now the VAB, which is inclined, is in the form of horizontal and vertical loading. VABX and VABY. I can write this as VABX and this one as VABY. 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 Come on, let's do one by one. When you do this diagram, you will get the answer like this. First one, I want the x component only. Let me take the x component which is negative. Start with negative, right? Because I take sign convention also important. I take this direction as negative, this direction as positive. VAC, this reaction. Now draw the diagram, which is negative and positive. Let me take in this direction because it's downward, right? So upward will be positive. Let me write the equation first, then we will calculate how much it is. I need to do this reaction. Come on, any other horizontal reaction acting on it? Go to the member. I have taken this component due to this reaction. Now we need to take this component due to this reaction. Let me take this one, B, point C. Please check if I make any mistake. Angle is 50 degree, right? And then similar to the last time, we have to mark the reactions, how they are vertical and horizontal, resolve into vertical and horizontal so that you can resolve them easily. Now draw the diagram, which is negative and positive. Let me take ACY. This is horizontal is VAC, X. Okay, horizontal. Now let me write down minus BAC minus VACX in this direction. So how much it will be? Or let me write the equation first, then we will calculate how much it is. I need to do this reaction. Come on, any other horizontal reaction acting on it? Go to the member. I have taken this component due to this reaction. Now we need to take this component due to this reaction. Let me take this one, point C. Please check if I make any mistake. Angle is 50 degree, right? And then similar to the last time, we have to mark the reactions, how they are vertical and horizontal, resolve into vertical and horizontal so that you can resolve them easily. Now draw the diagram, which is negative and positive. Let me take in this direction because it's downward, right? So upward will be positive. Same as the last time. I take the upward as positive. I mean the direction of my BCY, and then this one away. We've taken this direction, right? Let us take in this direction. So it will be BBCX. Come on. So we have another horizontal, right? In this, due to this reaction, can you see my mouse moving? Resultant can be resolved into. Can you see my cursor? See here, BC is cos theta. Theta is given already. Conveniently we can substitute. Negative is there. Plus. Same goes to the next diagram, which is this one. What do you have? You have this direction, right? I'm sorry, where we are? This thing, right? Yeah, horizontal. We need to take horizontal. So in this direction, it's positive. Our BCX will be again adjacent side, right? This one again adjacent side. So we will have VAC plus 0.643 VBC. Are you getting this answer? Equal to 0. Then moving on. Have you got the answer? Right. Treat this as equation 1. Now apply the second equilibrium equation, which says sigma Fy is equal to 0. All y direction forces equal to 0. Let's use this equation for both, okay? For both diagram. Let's take the first diagram, which is here. BAC, resolve all the y direction forces, right? Vertical forces. Sign convention is like this. This is x, this is y, this is minus y, this is minus x. Okay? Minus x. Minus x. Okay. I don't know why it's not stable. Okay, got it. Right. Now let's take this one. Where we are, we found already this one, right? We are at this point. We need the diagram. This diagram, first diagram, right? Let me take the first diagram and then solve one by one. Go for y, which is Y direction, this one, right? This one. Can we write down now? Or resolve all the Y forces. Again, there are only two forces acting. So the component of this one, VA, VAB, this is VAC, VAC. This is VAC, VAC, both are positive. So VBC also positive. Any other vertical load in this member? Come on. There is another vertical load which is 100 acting at this point. Negative or positive? Negative, because it's downward. 100 newtons acting, equal to 0. Right? Now we will solve all for all the forces acting on it. Hence we can conveniently move on to calculate the answers. What is VACY? VACY is VAC resultant times and the similar equations, the Pythagoras theorem we can use. Because it's opposite side, AC is opposite side, Y is opposite side, I use sin theta, sin 30 degree. I go quickly because you already know. VBC is, VBC again opposite side, so I do VBC times sin 50 degree, right? Sin 50 degree, sin 50 degree equal to 0. Okay, sin 50 degree is equal to 0. Let's do the solution. VAC, when you solve for sin 30, you will end up with 0.5 VAC plus C, and this one is C, 0.766. And we have two unknowns, right? AC and BC are our unknowns. You already arrive at the solution. By solving these two equations, you can get your unknowns done. How do we do it? Both are equations, right? Similar variables. So we can subtract 1 over 2, 2. 0.866, 0.866 divided by 0. Don't write it properly, please. Okay, then how much is this? 1, right? When you do that, substitute in 2, because I've taken 1, right? When you do that, you get it in terms of VAC, substitute in 1, substitute in 2, substitute 2, 3 in 1, substitute for 0.766 and then equal to what is, even if I take from text or anything or do myself also, there is an error. You need to. Finally, we have to find the stresses in the cables, right? This is the force developed in AC. Now we want BC, right? BBC. Or my letters are running value, which is VBC. Okay, VBC. The value of BBC is 87. Please check your answer, and similar to that one. 87.2 members AB and AC, right? AC and Y. Remember, AC is equal to VAC divided by the area. Better we find the area separately, or otherwise I substitute here ID. The cable diameter is same. Cable diameter is 20. Diameter 0.02 G. Please check your answer. You also do work along with me for Newton over meter square. Similarly, I can find 2BC is equal to BBC divided by pi d square by 4, which is equal to d square by, which is equal to 87.9 newtons divided by pi, same diameter. The both cables are of same diameter, so convenient for you to calculate the area in the beginning itself, so that you can easily substitute it at the end. I end up with Pascal's or Newton over meter square. With that, the calculation is over. Any question you can ask me. Let's stop here. Now we found out the stresses on the member. stresses on the member AC and BC. Sigma AC and sigma BC are on top. Okay. Any question? One we solve for forces on the member. Any question? Anybody? I'll share screen for 1 minute. If you have any question, you can ask me. Because to understand the questions that you asked me last week, we have to go step by step. That's why I brought this question. We do one by one, understand what is stress, how you're calculating, and then slowly moving on to finding the factor of safety. Are you clear with how to find out the forces on members? Which is inclined? If straight, you can easily find out, right? But incline means you have to resolve the forces into its vertical and horizontal direction and then find out the answer. Okay. Any question?
No, miss.
Okay, let's move on to the next question. Quickly solve for the next one also, which is something similar to that, but it is interesting if you go step by step. I cannot jump into the one. It's very simple, 3-line questions only, but still it needs good understanding of how you solve them. One moment. Right. Next question is on, you read this question. I didn't share it. One moment, I share this answer first. Okay. Let us go through this one. All of you read the question carefully. I change the font now. Font is very small. I take this question from the last year exam paper. Let's solve this one now. Share screen. It is not going. Okay. I think I got the share screen. Can you all see the screen? Right. Read the question. What is given to you? Anyone can read the question? It's very silent from your side. Can anyone read the question, please? What is given to you? Anyone is there? Oh, I have to call name.
Yes,
Take it.
miss.
Please, anyone, not Martin. Always Martin is answering. Very good boy. Others, I don't know what happened. Nobody is answering. Not alert, active in the class. Quickly read the question. Please make it interactive. Some questions for a few weeks I will solve. Later you have to come and then solve with the whiteboard, sharing a whiteboard and then pen and so on, right? And it is interesting. You are learning from your friends. You never forget in your life. Come on, read one of you quickly. Oh, this message also. Quick. We don't have time. I have plan to solve 3 more questions. I shared already, right? I think I shared. Yeah, it's there. Come on. One of you read the question loudly. Chong Zi Xiong. Can you please read the question? I don't know whether you are there or not.
Yes.
Second question. Please read the question aloud. Let the others listen.
A 6 mm diameter pin is used as connection C of the pedal shown in figure Q1. Knowing that P equals to 500 and determine the average shearing stress in the pin using a free body diagram and the normal bearing stress in the pedal at C and in each support bracket at C.
Okay. Understand this question? This is a cutter, right? Mechanical cutter. It has component parts, right? This is the cutter portion. And this arrangement is supported to an angle and to the wall by a rod, isn't it? Now you are asked to calculate. Can you hear me? Okay. You are asked to calculate the stress in the pins, right? the pin, the stress in the pin C, actually they have to give the name because the diameter of the pin C is given. Diameter of the pin is given. You're asked to calculate stresses in the pin and also nominal bearing stresses in pedal and the bracket. Okay, and you are given with the loading. The loading is not at the middle, they are applying manually at the end. If you see actual arrangement of this pin, you really have to understand the actual arrangement. If you understand this question very well, the second question will be very simple because I'm trying to get the real component for that as well. Let me see how much I can explain to you. Come on. This is, I repeat once again, this is a mechanical cutter. You are given with this arrangement. The cutter is positioned by means of this arrangement. What is it? Oh, the arrangement is like this. Let me turn to the pad. Okay, the arrangement is like this. It has a pedal. It has one moment. I increase the brightness, right? I write one by one the component parts. This is called as pedal, the lever that you can moving to cut with a knife at the end. And then this is this arrangement is called as bracket. Okay, bracket. I think they use the same word, bracket. And this is known as pin. This one, pin. This is known as pin. Please understand this arrangement. When you cut at this point, when you cut at this section, and then view, this is the elevation view, right? Elevation view is given. Elevation view of a mechanical cutter is given. Vertical elevation view. When you cut at this point, right? When you cut at this point, you have arrangement like this. When you cut and see the arrangement, you have arrangement like this, right? The component parts are, this is the pedal, right? This one is related to this. This one is related to this. This one is related to pin, right? What are the diameters given to you? The pin diameter is given, right? The pin diameter is given in this cross section. If you plot the diameter, this is the pin. The pin diameter is given, which is how much? 6 mm, I think. 6 mm. The diameter is given as 6 mm, right? And then when the diameter is given, automatically it is a circular pin, which is holding this bracket. The bracket is having the depth of 5 and the width to the width of the pin is already 6. And then another thing, the pedal is located like this to move by hand, like this. See this arrangement, move by hand, which is of 9 mm in the plan view. This is the plan view at the section there. When you cut at this section and look at the plan view, you will have this. At this point, it is the pin, right? Pin. And this one is the bracket again, right? The same bracket on both sides. Two brackets are there. First bracket and second bracket. And the pin both sides. You have the pin with this arrangement. And mechanically, you can see the arrangement like this. See here. This is the pedal, right? This is the pedal, the cutter with the knife. And this is the bracket. This is the bracket. And this is the pin, right? This is the pin. Okay, they are using this instrument to cut, right? Because the material, the what do you call this pin, the pin arrangement, when you move this pedal, it can shear along this diameter. See here, I take the red color one or some this color, because it can shear along this diameter due to the pin arrangement. When you move this pedal, because it can shear along this diameter to the thickness of this pedal, the material is cut, right? The application is in such a way that when the pedal is moved, the rod and the pin with this arrangement, pin with the bracket can move or rotate, right? Can rotate or shear in this diameter to the thickness of the bracket, or wherever you want to calculate the shear, you have to follow corresponding thickness and diameter. Because it can shear along this, right? Let me take the different color, yellow color. Because it can shear along this, and this, I cannot draw the circle. Because it can shear along this perimeter times the thickness of the material. In other words, rotation, you can simply say this as a colloquial term, rotation, because it can rotate, it can cut, it can do the job at the end, that is cutting. It has to cut the object that is kept here, right? It has to cut the object that is kept here or at the panel, right? This is what you have to understand first, so that when I do the calculation, you will understand clearly what should I take for your calculation of load and the stresses. Any question at this point how this is operating? Anybody? Shall I repeat it or is it clear?
Yeah, clear.
Okay. Now you understand what is pedal, what is bracket and what is pin. Alright. Lastly, I repeat once again. The pin has to shear along this diameter or rotate, right? So that it can cut the object. It can help to cut the object. It's doing some application. And the bracket, if you take this one, bracket, or we can call this as a what do you call it, a pad we say. Sometimes it's called as just a pad. The pad has to shear along how much? This diameter, again it is a circumference, right? Times the thickness of this one. Have to shear, have to rotate, have to move. Then only the job of cutting is done, and so on, and hence to the pedal. Let's understand, and with this understanding, do our calculation. What are the information given to you? Diameter of the pin is given, thickness of the bracket is given, thickness of the pedal is given, load is given, right? The unknowns are how much is the stress. I think there was a question asked. Let me check. Yeah, you need to find the shearing. See, it is already given us shearing stress. It is already given us what is the shearing stress in the pin, and then bearing stress. We call this as a bearing because sometimes the unit is called as bearing. It acts as a bearing. This is a bearing. Okay. Bearing, nominal bearing stress in the pedal. Right? How many pedals are there? Ongzia, how many pedals are there? How many pedals are there? Sorry. How many pedals are there? Ongzian, in this arrangement, how many pedals are there? It matters. Please answer me. How many pedals are there? Ongzian is there? I see always 100% attendance, but when I ask question, nobody answers. Maybe I'm talking about the old student. Oh, sorry, no Ongzian here. Tan Chi Ming. But Ongzian is a very good student. I remember the name. That's why I repeat once again. So sorry, you're not in this group. Tan Chi Ming. Can you answer
Yes,
me?
miss.
How many pedals are here in this question? Pedal.
2.
See the diagram, please. That's why I ask you whether you understood or not. See the diagram. How many pedals are there? Next. How many pedals are there? Lim Rong Ying. How many pedals are there? One pedal, right? This one pedal I written here. Can you see the screen? One pedal, right? Then what about bracket? Please answer, anyone. How many brackets are there?
Oh,
How many brackets are there?
we have 2 brackets.
Very good. I repeat, better I write down, otherwise you keep confusing yourself. Brackets are 2. Pins are 2 for this arrangement. Pedal is 1. Now you are asked to calculate what is the shearing stress in the pin, right? Shearing stress in the pin. What is, I just use other color. What is the shearing stress in the pin? Because it is shearing to the, one moment. Okay. What is the shearing stress in the pin? What are the bearing stress in the brackets and pedal? Okay, let's do one by one. don't know why it's turning everywhere. Hope you understand the data given to you and the arrangement given to you with that knowledge and its action, right? Where the action is going on, which component is in action for finding a particular type of stress, understanding the particular type of stress so that you can calculate and design and construct this particular product successfully. If anyone stress is more or less, either you will cut your hand or your job of cutting is not done properly. That is what will happen. So you have to design a proper one which will successfully cut the objects or the purpose for which it is intended for, right? Solution. Let's do the solution. The given data you please write down. I don't want to spend time on this because I have written here. I request you to write the given data when you do this calculation, but all these diagrams are representative for the given data, and these the information are given to you to find the unknown, the depth at which it is located, and then the width from the support to this pin, and the length of the pedal, all are given to you. Okay, let's solve one by one. Come on. Solution is very simple answer, right? Just 3 line only, provided you understand. We start with free body diagram. We cannot live without free body diagram, otherwise I cannot understand what is happening. Let's do the free body diagram. My handwriting is very low. Okay, start with members. What are the members? There is a support and there is a pedal, right? I do the split. The split is sometimes splitting very equally. I cannot even move the split. What is happening to this one? Right. The split is not moving at all. The split is not moving. Maybe I have to keep the cursor here. One moment, let me spend 1 minute on this. Okay, good. It's still half only. I cannot move it. I can move now. Right. Come on. My diagram is here. Let me do the free body diagram with the given data. Right. Start from here, which is very important diagram for you. Make it very clearly done. Start from here is A, right? A, B, right? And the location of A and B is given. And then what else is given? This member, I draw this member. Is only the support, so I just leave it like that. No need to bother about this one. And then for start from here is another C. You got C here and another member here going on, and the point is D here, and you have a load of how much? 500 newtons. What else is given to you? The distances are matter. Please draw the distances, right? What else? I'll just do the diagram here. Okay, because of the loading and the support condition here, there will be a reaction, right? There will let this reaction be FAB. For the whole of AB, you take it as FAB. I just remove this point, otherwise misleading you. Okay, the member is until this to this. So I take this as FAB, first of all, AB, because it's horizontal. And then because of this one, you will have another reaction, because the member is inclined, right? Member is inclined, you will have automatically a reaction in this direction, which is C. Let this be C. Okay, the response is in the inclined direction because of the inclination of the member. So I mark this as C in this direction. So because the action is like this, isn't it? It is cutting like this. The moment of the lever is like this. So when you do push it, the reaction will be in this direction. So I mark at C. Due to pin, it will react, and the reaction is equal to C. And then for this support, because there is another pin here, I mark this reaction as this one, right? FAB. What else you have to do? Is there any other forces acting on it? That's all, right? Load, reaction we mark already, support also we mark already. This is pin and this is also pin. Okay. We mark all the reactions due to this loading, right? We assume that Because of this, it is acting in this direction, and because of this support, it is acting in this direction, right? Because of horizontal member, right? Start from here. It's running always on. Come on, let's find how much is C, right? When you find the C, the reaction C, you are answering for the question what is the load and what is the corresponding reaction. Once you get C, your problem is solved, right? You are asked to find at C what is the at this point at C what is the stress produced by the pin and also the pedal and also the brackets, right? Brackets. Hence, I need to know how much the reaction taking place at this point. Let's see, let denote that by just C, and then draw all other information we have done already. Now moving on, resolve for finding the reaction we used to follow simple equilibrium equations, right? The mechanics of solids gives you the equilibrium equation, so we know that by applying sigma Fy is equal to 0. You apply this sigma Fx below sigma Fx equal to 0 and so on, right? If you apply these equations, you are able to answer for this question. Let's take one by one. Sigma, I put this diagram here, right? Okay. Now let's take the sigma Fx. Fx, if you take let me resolve the forces first and then we'll understand. Take the point C. How is it existing? One moment. Take the point C. Because it's inclined, you need to draw the forces acting at this point by resolving the forces. This is your CD, right? CD. And this is your P acting on it, right? P acting on it, right? And this is in this direction, or it is, just take it as a dotted line. Imagine there is a line joining. Maybe you have to remove that point, dotted line. It is not existing, just dotted line. When you join these two lines, because our dimensions are given, I go to this diagram, then you know why I am resolving like this. To understand this equivalent, right, whenever it is inclined, we resolve into vertical and horizontal, isn't it? Vertical and horizontal. Whenever it is inclined, you need to resolve them into vertical and horizontal so that you can solve the problem. But here, there is no angle given, right? But the sides are given. Because the sides are given, I am doing it this way. Taking this as a perpendicular. Because the sides are given, if you project this length, to this one, can you see my cursor moving? When you project this length to this one, you will have the value of 300 at the bottom, isn't it? I write here 300 mm. And then because this distance is given, you see my cursor moving, I can write this as 125 mm. No angles given, so I go by the sides. I take this value. Please listen carefully. If anywhere you are not understood, please ask me immediately. Right? Now we can calculate the value of C, P at this point. You can treat it as P or just leave it as the value there. Right? We are marking the load as P, isn't it? Better not use this word. DE. Let it be E, and the load P is acting at this point, right? How much is this? P. P is equal to 500, right? 500 units. Now CE. Let's calculate CE. How much is CE? By applying Pythagoras theorem, it is CD square plus DE square, right? So find out the answer quickly. Substitute the values and find out the answer, right? 125, 125. You can work along with me. The answer will be 325 mm. You can check the answer, right? Because arithmetic, please manage, because I need to do another calculation also. Right, we have done this part. Moving on, we need to find out how much is the force, right? Now we got this ohm value of C value, or the forces are resolved into different possible for resolving into vertical and horizontal. I got the hypotenuse already, right? 325 is my hypotenuse. Now I got it, right? Let's do this part by applying sigma Fy is equal to 0. Let me see first equation. If I can get the answer by Fy, then I stop. Otherwise, I would go for Fx. Let's do the sigma Fy by considering the triangle BCD, right? Where is it? I'll go for my triangle D. This one. This one. Right? Let's solve all the y direction values. Okay, y direction values. What are the y direction values? You take this inclination first. Sigma of y is equal to 0. Start from this value, the number 1, which is 125 over. Can you see from the diagram 125? This one. 125, right? The vertical component will be 125 over the hypotenuse is this value. Let me take this diagram. Hello.
Miss, can I ask a question?
Yeah, please.
May I know why the PNC have to be inclined? Why we do not just directly divide it into the y direction and the x direction like we learned in the previous class for the pin reaction?
There are ways of doing, but I follow this way to explain so that if at all, if any other question coming in, you can solve this way. You can also solve the other way. Yes. Directly
Because
can
it-
I'm going to do, but I'm explaining everything and then do the answer.
Okay, thank you.
Come on. I take this triangle, right? I don't know why it's running here and there. I take this triangle, like assume this is vertical and this is horizontal, right? This is my C, and I have to know how much is the RYC, right? Or just Y, let it be Y itself, because we don't use much of the data, only one point we are asked to answer. So you just use Y only, CY. Why is not going here? What happened here? CX. This is CX. What's happening? That's why I recorded earlier. What happened to this? Otherwise, I will show it separately. I have the C value in this direction, so I take the vertical and horizontal as CX and vertical as CY. Come on, let's substitute the values quickly so that we know what's happening. Let me move part by part. Right. In this case, resolve all the y direction forces. When you resolve y direction, you have only two, right? This is horizontal. You have only left with component at this point, which is just now we did it. Where's the diagram? It's running everywhere. Okay, draw it here itself. This is horizontal. Okay, this is horizontal, right? This is vertical. Okay, I take the vertical as CY, right? I do it CY. CY is positive or negative? Positive, going upward, right? And then there's another load which is 500, right? Which is 0. How much is CY? CY is equal to, let's calculate CY from this triangle, which is hypotenuse times, CY is equal to, CY is opposite side, right? Opposite will be, opposite side, CY, opposite side by adjacent side, which is 125, right? Opposite side by hypotenuse, right? So I solve the opposite side is 125 divided by, what is the hypotenuse value? 325. We already found out in this section, right? Just now we found out. I'll show you this one. Just now find out CE, right? CE we already found out. So it will be 125 divided by 325. When you substitute the value times C, that is important. Where is this one? CY is times C. That is important. Okay. So I substitute this value 125 times 320. Just solve this equation, you will get the answer already. 0, and then you end up with C is equal to 1, 2.6, 2.6. Directly I substitute already value there. 1300. Please check your answer. 1300 is getting. Now we solve for the first component part, which is unknown to us, right? We wanted the vertical load which is acting on this portion, Cy. We found the Cy. Next we move on to calculating the value of, you got the shear, the C value itself, right? We got the C value itself. This is the stress acting on it. This is a normal stress, is a normal stress. Because the components are known already, so we can directly substitute the value. Normal stress is given by C is equal to 1300 newtons. Done. We found the stress at this point, right? At this point, the load that is acting at this point. Now we can find the stress for different components. We can find number 1 stress at the pin, stress at the bracket, stress at the pedal. Start with stress at the pin. Normal stress at the pin. Let's find number 1. Having known the load, I can calculate all the other answers. Let me remove this. Okay. Start from pin. What is given to you? Diameter, everything you remember, right? The normal, usual notation we can use it, which is force over area, right? Force over area or C over area. Here we have the value as C, the load as C. We already found out C over area. C is equal to, how much is C value? 1300 already there. 1300 newtons. Area is, how much is the area of the pin? Anybody? Just answer please. How much the area of the pin? 6 mm, right? Area of the pin. How much is the area of the pin given to you? I mean the cross diameter of the pin. Diameter of the pin is 6 mm, right? So substitute the diameter of the pin, which is 0.6 or 10⁻³ also fine. So this is the diameter of the pin, pi d square by 4, isn't it? Pi d square by 4. But for the pin, one pin, stress at one pin, stress at one pin. If you want to calculate, then you divide by 2. I want this is a total stress acting on both pins. Stress at both pins will be this due to this loading. So divide by 2 will be giving you the stress at one pin. So how much is the answer? You are getting the answer as 23.0 into 10⁻⁶ pascals or 23 megapascals. Okay, that is the answer. Number 2. Let me move here. I don't know, my diagram is running everywhere. Later I will arrange it for you. I post to the CNI, correct it and post it. For now, just live with this. Where we are here, right? Here. I also have a solution to check cross. And start from here. Second test is to find the stress at the bracket. We do one by one, then go to the pin. Pin already done. Bracket, pedal and bracket. Stress at the pedal. The next object is stress at the pedal. Remember the pedal position and the big one, the cutter. The cutter. You have to remember the cutter. Maybe I show the diagram. Flip. The cutter is like this. You have to remember the cutter, this portion. You are now solving for this portion. Okay. All of you look at this pedal and then do the stress analysis. Okay. I don't know what's happening to me. Here. All of you be here to check the diameters, everything, so that you can answer properly. Come on. I'm here to find the pedal. Stress at the pedal. Stress at the pedal. Again, the same formula. Tau is equal to, I just say pedal. Force at the pedal divided by the area, right? All the forces C is acting at the same point, right? Where there is a pin. The pin is this way, right? The pin is this way. Pin is this way. There is a pin, there is a pedal, there is a bracket, there is a pedal, right? The arrangement of pedal. So you now calculate the area of the pedal at this position. Area of the pedal. So area of the pedal is just differ by the area of the pedal only, right? Area of the pedal. Now the force is 1300 newtons again, and it is spread over what? How much area of the pedal? You have to carefully substitute the pedal area. How much is the pedal area? Go to the pedal. This is the pedal, right? Can you see my arrow moving? I think you can see my arrow moving. This is the pedal area, which has carefully, think carefully. It is a diameter. This depth. This depth times the diameter. Am I correct? The pedal is in action, right? Is in action or bearing. At this point, the bearing stress is due to, or the bearing stress is produced to the area of, let me draw the diagram here, to the area of this much, right? Area of this much, where this is 9 and this is 6, correct? I repeat, to the diameter, the stress is produced to the diameter of, because that much material have to rotate to cut the object. So this is 9, this is 6, hence the area will be dt, diameter times the thickness of the pedal. Diameter times the thickness of the pedal, which is, I substitute a C itself. So I have 1300 newtons divided by diameter of the pedal, which is 0. Or you write it like this: 6 mm diameter of the pin, right? To the cross section of the pin, it has to work, and then across will be the width. Width is 9 into 10 power minus 3. Okay, so your answer will be 24.1 into 10 power 6 pascals, or 24 megapascals. Okay, that is the answer for the pedal. Let's move on to the calculation for, where's the enter point? Let's move to the third category, which is calculation of stress at brackets. Two brackets. So you need to divide, that's it. Brackets, right? Same formula, shear stress.
Miss,
Yeah.
the last one, do we need to multiply it with pi? Or just dt?
dt only, because it's a rectangular and the pedal is not a circular one.
Okay.
The pedal is not a circular one. It is given as, see here, the diagram it is given as the width, right? And it has to run through the diameter of 6 only. This is a plan view. This is the plan view. Just project it upward. You can see it's a kind of a rectangular portion. D into thickness. And then coming here, brackets. Come on, look into the brackets. You need brackets. This is bracket. This is bracket. I remove this point so that I will draw for bracket now. Now, stress calculation. Same formula. You write down the formula. Tau bracket is equal to force that is acting at C times over the area at the bracket. We know that is C. Area, how do you define the area? Come on, I don't know whether it's a D or a pi. Let me check first. Go to the bracket. When you go to the bracket, how much is the diameter arranged here? Check the diameter. Here? Where is it? Here. So it has to act, it has to act again to this, right? I remove this one clearly. It has to act to this thickness on both sides, and two later we do the 2 or 1 later, but now see that the brackets are like this, isn't it? It has to work for this thickness, this diameter to the thickness of 9 mm, correct? The bracket have to work 5 is the thickness given to you already. 5 is the thickness given to you already, so you can work for times the thickness. So just multiply and give me the answer. Can you do it yourself? Because there are two, you have to divide by 2. You are asked to find out the each or both, brackets both or each. See the question? Each support and each support bracket, that's each only, so you divide. All right, so now come on, area, how much is this? Dt, again it is dt, d into t. The width is given, it is not given as diameter, it's given as a what do you call, a bracket. So I substitute this as 1300 newtons divided by d is 5, right? 5 into 10, 5 mm again, 5 into 10 power minus 3 times t. It has to rotate or cut through this, shear through this much thickness. Thickness is 6. It has to run through the thickness of the pin, which is minus 3. So the answer will be, what is the answer you are getting finally? The answer is 21.7. All are almost near, close to the answer. 21.7 megapascal. Okay, that's all. I mean, this is double times, right? This is double times, so you have to divide. This one, you have to, the area need to divide. Divide will be multiply. Okay, when you multiply, you will have, when you divide the area here, then it will go up. So you will get the answer as 21.7 megapascal. So this is the stress at one pedal. Okay, I stop here. Any question you can ask me. Just go through the calculation once again so that you will understand it well. You are given, I repeat, you are given with this arrangement, only one load is acting, right? If two load is acting, you have to provide the counteractions or reactions and then find out everyone. Now only one load is acting, which is borne by this, right? Supposed to be borne by this, because it's inclined and the member is inclined, or if you project it perpendicular to this paper, you will see the arrangement like this. Okay, it's inclined, so hence the reaction is acting in an inclined direction. We resolve based on the dimensions given, otherwise we don't resolve like this. Okay, because the dimensions are given to you, we resolve into horizontal and vertical to get our first answer of this component. Okay, triangular formula. We got the formula, I mean the value of the hypotenuse. With that, we use this equation to get our Cy done, right? Once you get Cy, right, which is acting vertically, which is in action for the stresses produced, right? There is no horizontal force acting on it, so there is no horizontal moment or the reaction effective in this cutter. That's the point you have to remember, why I didn't bother about, or it is not needed for worrying about the horizontal direction, only vertical direction because of the vertical load and the support condition. So we resolve this one, resolve all the vertical loads. We have Cy, because it's inclined, I take the Cy component in vertical direction minus the load, rearrange, you will get the load in this direction, end up with C, the load in this direction. Okay, and then we followed one by one for calculating stress at the pin, stress at the bracket, stress at the pedal. I stop here for this question. Any doubt you can ask me now, otherwise we move on to the third question, which is important for you. Okay, later I will arrange it and then post it in your CM for referring. Any doubt?
Miss, for the pin and also the bracket, why we need to divide by 2?
Because two brackets are there,
Oh.
right? Yeah.
So we
have to
the
divide
error
the
times
stress
2.
by, we have to divide the stress by 2.
It means like it experience like a double shear stress, right?
No, there are two brackets. See there are two brackets, right? If the load is acting, it will be shared by two brackets, right? The load will be shared by two brackets. That's why we have to divide. Same like the one we did it in pins. Pins also we divided right? We divided the load. Wait, I repeat, I take the screen and then show you. View split, remove split. Okay, come on. I repeat this one. Okay, when you go here, there are 2 pins and 2 loads, isn't it? In 2 pedals, right? There are 2 pins. I remove you. It's running like this. Okay, let me remove this one. I don't know why I cannot remove it. Leave it. Oh, come on. See here. There are 2 pins, right? There are 2 brackets and 2 pins have to be there to fix it, isn't it? On the other hand, pedal will be only one to cut. Because there are 2 pins, the same load, when I put it perpendicular, the C is acting at this point, bound by or shared by 2 brackets, shared by 2 pins. Okay. To find the stress, you are asked to find each support, each pin, right? That is why you divide the stress by 2, or you can either divide the load or divide the stress by 2. I do it here, where is the pin? Yeah, pin here. I do it here because this is pi d square by 4. I do it here, divide by 2. See this one? Hello. Understand? The load needs to be shared by 2 pins and 2 brackets. It's too difficult arrangement. Okay, who asked the question? Did I answer your question? Pin is done. And then moving on to bracket, same problem. 2 brackets are there. That is why I divide by 2 here. It's a divide. It should be divide. Should be divide. Because the same load is shared by 2 brackets. So I need to divide. When you divide, you will get this answer. Please check once again. Alright. Let's move on to the next question. Clear? Are you there?
Yes, clear.
Okay, thank you. Let's move on to the third question, an interesting question. Let me share this. You have to have imagination when I say, otherwise it's still difficult, cannot understand at all. Right? Very interesting question. Come on, let me read this question. I don't have time to let you read. You are given with 2 vertical links, okay? 2 vertical links, BE and CF. Connecting 2 horizontal members, connecting 2 horizontal members, AD and EF, has a 10 by 40 mm cross section of AD and EG members are given. The beam or members are given. Okay. And of uniform rectangular cross section. Note this point for finding area. And are made up of steel. And have a tension of this. Strength is given. Each pin at C and F has 20 mm diameter and are made of steel again. All are steel, don't worry, but of different strength. Links are having different strength. Members are having different strength. Or beams are having different strength. 2 beams are connected by 2 links to make a roof, or maybe a bottom of the roof, support for the roof. It may be a girder. They are using all steel. Find out the overall factor of safety. How much more you can load. Right? How much times? Either 2 times, 2.5 times. When with this strength, right? With this strength and the load given in the diagram, you need to find how much factor of safety is required to design this member with this cross section, with this diameter, and so on. Okay, I go to the diagram there. See, you must have a really a good imagination power. Otherwise, you cannot answer this question. Okay, start from here. You are given with, this is the member, member 1. Member 1. You may hand it. This is member 1. Okay, and this is member 2. This is member 2. Understand first the given data, and then 2 links. Link 1, link 2, pin 1, Other side also, another, I mean this side if you say there is a pin which I cannot mark for you now, but if you look at the plan view you can see it. Like the last time, I don't do it every time. Please imagine yourself like the last time. That's why I brought that question for you. Pin 2, this is pin 2. Okay, and then what else you have? This is also pin, right? Pin 1 and pin 2. This side is pin 2. Inside you can see pin 2, right? Now you are asked to calculate only at this pin for this link CF, right? The point of interest or the purpose of calculation in this question is to find what is the overall safety for the link CF, right? When you ask to design only CF, concentrate on CF with this arrangement. Find out the load, find out the stress, find out the ultimate and applied stress. With that you can find the factor of safety, because factor of safety is defined as, all of you remember this, factor of safety is defined as ultimate stress to applied stress or design stress, right? Ultimate means the maximum that it can bear, okay? Ultimate stress to applied, this one applied, ultimate is given to you for both link and member, right? Are you clear with this arrangement? And then we are going to find, you are asked the number, I repeat once again, you are asked to find the overall safety at, factor of safety at CF. CF is this member. CF is this member. Okay. Let's find one by one. Very simple question if you understand it. Solution. Write the free body, given data, please do it yourself. Write the given data, free body diagram. Free body diagram. Diagram looks like this. If you want me to recall split, easy. Let me reduce the size because for your learning only I made it very big. Now you understood what is it. Okay, right. Come on, draw the free body diagram. There we are. Factor of safety done, and this one also done. Come on, we are here. Right. Start from here. Draw the free body diagram. Start the member. You are asked to find the value at this CF, right? See, when it is loaded like this, support here, right? When you found the values at this point, right, also similar to this one. So I just take this member. This is loaded upon this one, right? Let's do this member first, right? Let's take this member EFG. Let's take the EFG member first, because you are asked to find out the stress at the pin for joining these two member for AD and EG, and it is connected by C and F. Let's take this member first, which is at the bottom, CFG. When I draw the free body diagram, start from here is like this, okay? E, F, pin, all pin, and G. Equal distance, right? Not equal distance, different distance. This is 0.4 meter. This is 0.25 meter. Hey, meter, right? Yeah, meter. Mm, I changed to meter already. This one B, ECF, ECF. EFG, EFG. Right. What are the loads coming in? This one, point load. The load is acting at this point, 24 kilonewton. Because of the load, there will be a reaction. Where will be the reaction? Anybody? Anybody quickly? Where will be the reaction? Where you will get the reaction because of this loading? Quickly. Reaction at this point, and then this another pin, right? Should be shared by this pin also. Am I right? It's a pin, right? It's not fixed. I mean, even fixed also you have a reaction. So this load should be borne by two pins. Maybe we do not know whether it's upward or downward. Because it's downward, have to be shared by either two equal upward or one big upward and less download, or very big and low. It compensate, these two compensate to bear this load, but in opposite direction. That is what assumed to be, right? Okay, come on. Any other I missed out? All are there, right? I take this as reaction, or just take it out. take it as just A or E or VF, VE and VF. Easy for me to remember. Come on, let's move on. We have to have the value of these forces in this member, right? To understand this, you can either solve by sigma F X or sigma F Y or sigma M. Anything you can use it. But convenient way of solving is it's already pin joint, right? It's already pin joint and it's a member acting. It's a load acting in this direction. It's not axial load, right? It's a load acting perpendicular, right? Perpendicular to the direction. It is easy if you solve by sigma M equal to 0. Take the equation which can easily solve, which has less number of things to consider, right? Either you can solve sigma M because it's a pinion, right? Pin, right? Pin, all pin. Okay, so at the pin you already know sigma M is equal to 0, right? The moment is equal to 0, right? Sigma M should be equal to 0, or moment at F should be equal to 0, moment at E is equal to 0. It's already pinion, right? Now, can we resolve the moment at any one point, either E or F? Okay, now let me take at point E. All the moment should vanish at E. That is the purpose. Okay, that is the purpose. Better sigma I put, right? Because it's pinion. Meaning what? There is no reactive moment produced by the body because it's pin. It can easy to move, easy to rotate. Okay, the split is troubling as I remove the split. Because it can freely move, you can always take this as 0, this as 0. Either you can solve all sigma M F is equal to 0, MF is equal to 0, or sigma M E is equal to 0. Both way is okay. Both answers should be vanishing, right? Let's do one by one. Number 1, start from here. You follow the things I already explained to you. Consider a clock. If you want the moment from this side, consider a clock which is 12, 3, 6 and 9, right? All clockwise moment positive, anti-clockwise negative. Start from this load. 24 is my load. How much is the load? 24. I start from here to this one because I'm resolving about ME, right? 24 is clockwise or anti-clockwise?
Clockwise.
Clockwise, positive. Times how much is the value?
165.
Add this one, 0.4 plus 0.25, right? 0.65 you can directly write down. Any other force acting this one? I assume to be in this direction, VF assumed to be in the upward direction. How much is this? Positive or negative? Negative and negative VF times. Are you following? Any mistake, please correct me.
0.4.
How much? 0.4. Any other force acting? Nothing else. No UDL or any point load before this. So I solve here. So I get a VF is equal to, how much is it? End up with 39. Are you getting 39 into 10 power 3? I just take from the solution. Hope you are also getting the same. VF should be equal to 39 times newtons. Okay, then followed by whether it's a tension or compression link. Anybody? See, when this end is pulled, it will get extended, right? There is a kind of a extension in the member, right? It will get elongated a bit, right? Elongated a bit. The member will get elongated a bit. So it is a kind of a tension member due to this loading or pulling effect at this point. So I can also call this as a tensile stress produced by the body. Okay, tensile stress produced by the body. Before I go to calculate the tensile stress, what is the area of contribution? That is most important for you. Okay, what is the area of contribution? Go to this member, the diagram. What is the cross section given? Cross section is given as 10 times 40, isn't it? 10 times 40. The other dimension is, let me draw the diagram so that you are clear. When you draw this, we are now talking about this panel, right? I mean, at this point, we are talking at this point. When you draw the diagram for this one, it will be The cross section will be the cross section which is in action, right? When this is pulled, the cross section which is in action will be like this. 0.4, and the dimension is forgotten 10 times over. 10 by 40 is EG. 10 by 40 EG. What's the value given? AD and EG. AD and links, AD and member only. Member cross section is this cross section. This cross section is 20, the 10 by 40, isn't it? This is 40, right? This is 40, and the other dimension like this. This is 10 thickness. This is the inside inner thickness. Inner thickness is 10. One moment. Inner thickness I go by this way. Inner thickness is 10. 10 mm. This is 40 mm, right? This is what given in the question. The links are 10 by 40 uniform rectangle, right? Perpendicular to the slide is the paper is 10. Width is or depth is 40. So this portion is in action to the thickness of this, isn't it? And then we do have three arrangements, right? Like the last time, one member, one pin, and another pin, right? These three are in action, right? They are connected by this pin arrangement, right? This member, and then this brackets and the pin. I repeat, this member, and this is this bracket, and this is this pin. Remove so many arrows. Okay, this is the pin. Okay, so you have three arrangements. You need to calculate how much is the contribution to this shearing, right? Or what you call, not shearing, I'm sorry, the extension, the member which is in action will be B times D, but B is not full B. The full width is not contributing, right? When you draw in another diagram, the full width is 40. Full width is 40. This diameter, how much is the diameter of the pin? Diameter of the pin is, Srila, I don't know where it will, maybe in the diagram.
20.
20, which is given 20. 20. Diameter is 20, right? Hence, the net portion which is in action, right, which can be extended will be the net portion which can be extended will be this portion, right? This portion, right? This portion. So I write it like this: the area which is in action for this force, net area will be B into T, which is 40 minus 20 is my B, right? And the thickness is to the diameter of the in this portion, this one, and this one, this thickness to this thickness into thickness of the mm, all in mm. So the portion which is in action will be to this depth, to the width perpendicular to the slide will be thickness of the member, which is subjected to this tensile force, right? I repeat, due to this loading, due to this download loading, right? Due to this download loading, the member which will get extended will be like this, and the whole portion. We are asked to find the stress at this point only, right? Stress at this point. So when you calculate the stress at this point, it will be a portion which is available, net portion available at this point. To find out how much the net area which is contributing to this load will be, I have taken this section separately, right? The member, it is the member. Where I will write it as a member. The rest you will not. This is the member. Member or FG at point FG. At point FG, you have the member like this. You have the pin. This is the pin. This is the pin. You have the pin. The depth of member FG is 40, and the pin is 20, right? Projected view, I take this one, projected view. This is the view I have taken. And then perpendicular to the paper is 10 mm because this thickness is 10 mm. That is what I am calculating here. So let's use this area here where we are. Now I can conveniently calculate the area or shear force, directly substitute in the shear force. Shear stress at this point will be given by area is equal to area of the link, right? Area of CF contributing to this load will be B minus D times T, which is B is 40 mm, 0.04 minus 0.02 times 0.01 because 10 mm. The answer will be 200 into 10 power minus 6 meter square is the area, right? So meter square, CF in action. I got the area.